So in this video, I'm going to go through my work solutions for November for Book 2 from the Daily Workout. So just maybe talking through the first one. The first one is fairly straightforward, just to warm you up into it. I just drew a quick sketch diagram, which is really useful to do. I just labelled, for my own benefit, the adjacent, opposite and hypotenuse, and then theta is equal to 56 degrees. So this one over here, just a really nice simple example. Number 2 was just a bit of recall in terms of what are some of the units. So these are things that you just have to remember off by heart. You need to know that momentum is kilogram meters per second. You need to know that EMF, the electromotive force, is also measured in volts. Magnetic flux density is something you won't cover in year 12, but you'll be doing it in year 13. And you might be familiar with this from the work you did at GCSE. Now for the next one, I think it's always really useful to label and actually add stuff to the diagram that we've got here. So we've got 9 ohm resistors, which I've just labelled here. We've got a battery of EMF 3.0 volts. And that means if we were to maybe consider the total resistance of this circuit, we can look at the combined resistance of resistors in parallel. So we've got 9 ohms, 18 ohms and 27 ohms. When you do this thing here, we can find that the total resistance of this circuit is 4.909 ohms. Now, the power is going to be equal to V squared over RT, which in this case is 3.0 squared. That's the EMF, or the voltage, divided by the combined resistance of 4.909, which gives a value of 1.8 watts to two significant figures. Now, again, there's different ways you could do it. You could maybe work out the fact that we've got the power in this resistor, and if we know the PD across it of 3 and the resistance, we can work out the power there. We could work out the power of these individually. There's loads of different ways, but ultimately we will get to the same answer of 1.8. Right, on the second, this one here is using a graph. So to calculate the acceleration of a velocity time graph, we're going to calculate the gradient. The first one, we have a straight line, and I drew in this triangle here, and you need to make this, you actually need to draw it onto the graph and draw it as big as possible. Now at 2 seconds, it's the gradient here that we're needing, so that's going to be equal to dv by dt. I put my calculation in here. I read off very carefully an approximate value from the graph, and this gave an acceleration of 1.6 meters per second. For the next one, at 6.5 seconds, we can see there's a bit of a curve. So what I did was I drew a tangent and I kind of judged this by eye, trying to get something which is approximately right. When I had that tangent, I then again worked out the gradient. Here, that's equal to minus 1.1. So don't forget, if we've got a negative gradient on a velocity time graph, we're going to have a negative acceleration of approximately 1.1 meters per second. For the second part of November, this one over here, we wanted to calculate the displacement, and that's going to be equal to the area underneath the line on this velocity time graph. And I just did it by dividing it into these different shapes. I also saw that a small square is going to be equal to half a second times half a meter per second squared. So the first thing I did was I worked out the total number of small squares, which is 138.5. And then I divided it by 4, because effectively one of these large squares here, which is 4 small squares, is going to be equal to 1 meter per second times 1 second. So that's why I divided it by 4 to get 34.625, which is about 35 meters. Okay, hopefully that's all going okay so far. Now, the 3rd of November, I decided to introduce something which is maybe something that you haven't done before at GCSE. This is starting to look at uncertainty. Now, this box here has some information which is applicable to all exam boards. Basically, we're looking at percentage uncertainty in a single measured value, and that's actually equal to the absolute uncertainty in that measurement divided by that measured value, and then you multiply it by 100. Now, this is where, for example, if you knew that there is an uncertainty, and here, this number here is the absolute uncertainty of 0.1, and that's often quoted to you in any exam questions. We're going to divide it by the measured value, which is this 12.5 over there. So the absolute uncertainty is 0.1 of a centimetre. I've divided it by 12.5, 12.2, and that gives a value equal to 0.82%. And I've decided in this book here, for sort of consistency, to give my uncertainties to two significant figures. So that's right, 0.82. Now again, depending which exam board you do, depending how the question is actually structured, they're going to be very clear about how you actually present that final answer. So the first one, question number 1, I've simply got my measured value, I've got my absolute uncertainty, and then I've just followed this thing here of dividing this number by this number, multiplying by 100, and then giving my answer to two significant figures as it's asked me to there. So that's how we got through this. Okay. Well, question number 2, determine the amplitude and time period of the following wave. So the amplitude is going to be the distance from no displacement, or its mean position, to the position of maximum displacement, and it could be either positive or negative. So this is the amplitude, which I've read and judged to be about 1.8 millimeters. Now the time period, you could just look at the time, maybe between one peak and another peak, or just for one wave cycle. But the best way to do it is to take as many wave cycles as possible. And I can see here that over 4 complete cycles, we've got a time equal to 9.5. And that means the time for one cycle is 2.375, which is about 2.4 seconds. And again, I think because I can really read something here to maybe two significant figures, like 9.5, I think I'm justified in giving my answer as 2.4 seconds. Okay, the 4th of November, we're going to do even more work on percentage uncertainty. So again, we've got the measured value and the absolute uncertainty that's been quoted, and you just divide this number by that number and multiply by 100. You can see that we might have sometimes the same absolute uncertainty in the measured value, but depending on the measurement that we're taking, we're going to get vastly different percentage uncertainties. So this would mean if, for example, you were to use a meter ruler to measure something about 8.2 centimeters long, we'd get 1.2%, whereas if we use the same meter ruler to measure a large distance, the percentage uncertainty, the error in the answer is going to be much less as a percentage. We then have a definition of Ohm's law. Ohm's law says basically that the PD across a component is directly proportional to the current through it at a constant temperature. Okay, so that is a good definition of Ohm's law, and you just need to know these definitions. The next one, determine the amplitude, time period and frequency. Well, again, the amplitude is going to be read off the graph directly, so this was 1.5 millimeters. The time period for one cycle is 4.5 milliseconds. And often when we're looking at waves and things, we often have very, very short time intervals. And the frequency is just equal to 1 divided by the time period, which here gives an answer of about 220 hertz. So 2.2 times 10 to the 2 hertz. On the 5th of November, just a simple bit with a triangle again. You're going to see so many triangles in A-level physics, and 99.9% of the time they're going to be lovely right-angled triangles. So I just drew a quick sketch diagram. We can see that the hypotenuse is 6.5, the adjacent is 3.1. We want to work out this angle theta. I just did a quick sketch diagram. We know that cos theta is A over h, and therefore theta is 62 degrees. The next one is a question about uncertainty. So now we've got a diameter of 0.42 millimeters, and that's going to be the measured value, and here the absolute uncertainty is 0.01 of a millimeter. We also have for the length the absolute uncertainty of 1 and the measured value of 40 centimeters. So again, we need to make sure that we convert the units so they're consistent. So we can see here that 40 centimetres is 400 millimetres. We then just use the equation that we saw over the previous couple of days to find that in the diameter there's a 2.4% error, and in the length it's only 0.25%. So here the biggest error and uncertainty in the measurement is due to the diameter of the wire. We then have a kind of a picture of the front of an oscilloscope. Now, when you do use oscilloscopes, they can be the most frustrating thing because a lot of the time it's really hard to get a lovely signal. But what you can do is you can adjust the time base, which is basically the x-axis, and you've got the y gain, which is the y-axis. And what you want to do is have something where you can actually take good measurements. Now here, the time base is set at 50 milliseconds per division. So that means between here and here, that's equal on effectively a t. The time is on this x-axis over here. One small division of 1 square is equal to 50 milliseconds. And what you can do is you can just adjust the knob to kind of basically spread or kind of get that wave closer together. The amplitude over here is can be read off the y-axis, and effectively each of these divisions up here is going to be equal to 1.0 volts when it's set like this. So to work out the amplitude of this signal, we can just say that's equal to 2.5 squares times 1 volt, which is 2.5 volts. In terms of the time period, well, if we were to look at the time for one wave, it's going to be equal to 6 small squares. Each square is 50 times 10 to the minus 3 seconds, and therefore the time for one wave cycle is 0.30 seconds. So this is how to read an oscilloscope, and that's why previously I just asked you to look at maybe the amplitude and period and frequency of that kind of wave on a graph, and an oscilloscope basically allows us to display that graph. 6th of November, we started again just with a triangle. This time we're going to use tan to find that the adjacent side is equal to 53 centimetres. That sounds quite a lot, but then if you look at the shape of the graph, if we think that the angle theta is only 10 degrees and we know the opposite side is 9.5, we'd expect this adjacent side to be pretty long. Now the next one, we've got laser light incident on a double slit and it's projected onto a screen. So this is an experiment that you will probably carry out in year 12. And what we have here are 11 fringes of light. Okay, now basically this total distance from here to here is equal to 5.4 centimetres. First of all, the percentage uncertainty, well, the absolute uncertainty is 1 millimetre. The distance measured was 54 millimetres, and therefore the percentage uncertainty in this measurement here was equal to 1.9%. So the absolute uncertainty of 1 divided by the measured value of 54 millimetres times it by 100 is 1.9%. Now the spacing between each fringe is going to be this distance over here. And therefore all we've got is 5.4 centimetres or 54 millimetres divided by 10 to give the spacing between each fringe as 5.4 millimetres. Okay, so 5.4 millimetres between each of those. State the percentage uncertainty in spacing between fringes. So the percentage uncertainty in the spacing between fringes is going to be the same as the percentage uncertainty in that total measured value. And therefore this 1.9% here is repeated down here. So what we have here is we've got the percentage uncertainty in a big value, and we're going to have exactly the same percentage uncertainty in the individual readings for those fringe spacings. Hopefully that's making sense. Maybe I didn't explain it so well. Okay, we've then got some definitions. Wavelength is just the distance between two adjacent points that are in phase on a wave. Monochromatic light is light that has a single wavelength. And a great example of that is the laser light that we use to actually shine through a double slit in order to maybe measure the wavelength of that light. And coherent waves are waves that have a constant phase difference. And we often look at coherent sources of waves which interfere, which again will give rise to patterns like this. Again, that's something you're going to be covering a lot more as you do A-level physics. The 7th of November. The first one is just looking at the mean value and the range of this tabulated data. So to work out the mean value, you just add all of these together, and then you just need to divide by 5 to give your mean value. and the range is going to be the difference between the largest value and the smallest value. So here the largest value would be 86.06. We then take away the smallest value, which is 82.57, and that's going to give you the range of readings there. Now this is quite repetitive, but there's a good reason why I ask you to do everything in this book. Okay, so we just work out these values here for the mean and the range. Okay, the wavelength of light is investigated using a double slit. The slit separation is measured using a travelling microscope as 0.60 plus or minus 0.01 of a millimetre. So a travelling microscope is something that allows us to take really accurate measurements of a distance, for example, something which is less than a millimetre. Okay, now the percentage uncertainty is just going to be the absolute uncertainty of 0.01 divided by the measured value, 0.60, multiplied by 100, which in this case is 1.7%. We then have another question about oscilloscopes. Now we can see that the Y gain is set as 0.5 volts per division. So each one of these squares is equal to 0.5 of a volt, and therefore the amplitude, it's going to be about 3.5 squares times 0.5, which is 1.75, so about 1.8 volts. So 1.7 or 1.8 is an appropriate answer for the amplitude of that wave. The frequency is going to be 1 over the time period. We can see now that the wave is 6 squares along, but we can also see that each square is 10 milliseconds. So I've got 6 times 10 to the minus 3 for our time period, and then 1 divided by that gives an answer of 17 Hertz. Again, I've just given these both to two significant figures, which I think is appropriate for reading the data from that oscilloscope trace. On the 8th of November, you need to calculate the mean value and the range of the following bits of data. Again, that's fairly procedural. It's just a case of plugging it into your calculator. You might notice, of course, that for A and B, we have exactly the same mean value. But here we can see that the values for B are a lot closer together. They're all about 8.4, so 84 point something, and therefore the range is quite small. Whereas for A, even though the mean value is the same, we have quite a spread of data, and therefore there's a bigger range. And that's going to be useful later as we come on to something else. Okay, we now have an investigation into the Young modulus, sometimes called the Young's modulus. And basically we have a thin piece of wire that's stretched. Now, that's something you're going to be doing in year 12. But for this question, we're really looking at the data. They're using a micrometer screw gauge to measure the diameter of the wire. And here we've got an uncertainty of 0.01 over a measured value of 0.42. So when we calculate the percentage uncertainty, it's 0.01 over 0.42 times 100, which is 2.4%. Now, that's going to be the uncertainty in the diameter. And to work out the radius is just going to be equal to the diameter divided by 2. And therefore, we'd have exactly the same uncertainty in the value for the radius of this wire as well. Okay, so that's basically a measured value, and this is going to be a calculated value where we just take this number divided by 2, but we still have the same percentage uncertainty in our measured value. Number 3, you will hopefully be doing lots of this stuff in A-level maths if that's what you've chosen to do as well. We've got a ball thrown vertically up into the air. We've got an initial velocity of 5. How long will it take to return to its start position? Well, for this, I drew my diagram, which is the ball going up in the air through a distance of s. I've said upwards is positive, and initially it has a value of u going upwards. I then wrote down suvat. Always write this down and then start to fill in what you know. So we know the initial velocity u is 5. We know when it gets to the highest point, the velocity is going to be 0. And we know that the acceleration is going to be minus 9.81 meters per second squared. And it's going to be minus because we're saying that upwards is the positive direction. We want to know the time it takes, and therefore we can use this equation here, v equals u plus at, to say that t is equal to v minus u over a. We've got 0 minus 5 divided by minus 9.81, giving a time because we have two negatives here that cancel out, of 0.5097 seconds. Now that's the time to get to the top, so the total time is going to be doubled because it also takes the same amount of time to fall back down to the ground as well. And here this gives a value of 1.0 seconds, which is to two significant figures like the raw data that we've got up here. And this is assuming there's going to be no air resistance. So if there wasn't any air resistance, you threw a ball up in the air, it would take a second to go up and then come back down again. On the 9th of November, we introduced something new, which is percentage uncertainty if you take repeated measurements. Now, to work this out, we're going to use the formula that says the percentage uncertainty is equal to half the range divided by the mean value multiplied by 100. So in the example I've got here, we've got 4 bits of data. We can work out the range by looking at the difference between the largest value, which is 23.4. We're going to take away the smallest value, 22.9. to get 0.5, and then we're going to divide that by 2. So half the range is equal to 0.25 millimetres. Now the mean value, calculated as normal just by adding them all up and then dividing by 4, is 23.175 millimetres. And that then means the percentage uncertainty is this value divided by this value multiplied by 100, which is about 1.1%. And this basically tells you that if you've got a larger spread in your data, if you've got a large range of results, you're going to be less certain about what the value should actually be. So, question number 1, calculate the percentage uncertainty in the following data. We've got some values, we've worked out the mean, we've worked out half the range, and then we've just divided this by that, multiplied by 100 to get 3.6, 1.2, 5.0 and 11. And that's the reason why I had you working out the mean and the range on previous days. Okay, so what we can see here is that for A and B, we have exactly the same mean value that you might use in a calculation, but they've got a different range, and therefore we've got a different percentage uncertainty in the results. So we can see that when the results are a lot closer together, we're going to be more certain and there's going to be less error in those readings. The next one, we've got a cheetah accelerating from rest to a velocity of 22 metres per second in a time of 3.5. Again, this question about motion, write down SUVAT. We know that initially it was at rest, so U is 0. It gets to 22 in a time of 3.5, and we want to calculate how far it's travelled. So I'll just put a little question mark there. We're going to use this equation here that doesn't have an A in it. We put the numbers in. The magic happens in your calculator, and we get a value of 38.5, which I'm going to say is 39 metres to two significant figures like the raw data. So SUVAT, always write down SUVAT, and you will get the answer correct every single time. I guarantee it. We had some real data, so again, we worked out the mean, worked out half the range, and used that to work out the percentage uncertainty. For this one, though, we had an anomalous piece of data. 84 was very different to all of the other values, and therefore this has been discarded before I calculated the mean or the range. And that's something just to keep in mind. This is the kind of thing they will throw into exam questions. They'll put an anomalous piece of data there that you need to identify as you're doing your work. Okay, Kirchhoff's first law is about conservation of charge, and it basically states that the current into a junction is equal to the sum of currents out of a junction. Whereas Kirchhoff's second law is due to conservation of energy, and it basically says that the sum of EMFs is equal to the sum of potential differences around any closed loop in a circuit. Okay, the next one, is this homogeneous or not? So energy is equal to momentum times the speed of light. Is that homogeneous? Well, what that means is the units on both sides equal the same thing. So first of all, energy, we measure that in joules normally, but what are the base units for energy? Well, we could work out energy by maybe looking at kinetic energy. It's a half mv squared. The units of mass are kilograms. The units of velocity are meters per second. And that means the unit of energy is a kilogram meter squared second to the minus 2. So that's basically the base unit for the joule. Now, normally we think about momentum as kilogram meters per second, and c, the speed of light, will also have units of meter per second. So if we're to multiply this unit by this unit, that's going to be equal to kilogram meters per second times meters per second, which is therefore equal to kilogram meters squared second to the minus 2. And what we can see here is that this is equal to this. So energy and momentum times the speed of light both have the units of kilogram meters squared second to the minus 2, and therefore the units match on the left and the right, and therefore that is a homogeneous equation. Okay, 11th of November. Something to remember. Right. A progressive wave is the kind of thing we'll have seen at GCSE. You're very familiar with it. And a progressive wave transfers energy from maybe one store to another, from one place to another. A transverse wave has oscillations that are at 90 degrees to the direction of energy transfer. So most waves we look at, electromagnetic waves, maybe ripples in water, can be seen to be transverse waves. Now, what we do at A-level is we start to investigate standing waves on the string. A lot of you might have done this at GCSE without really understanding how it happened, why that allowed you to measure the speed of a wave in that string. But this question doesn't really ask you about the physics, it's about the measurements which have been taken. So, the percentage uncertainty in the measurement is going to be equal to the uncertainty of 0.4 divided by the measured value of 22.0. So here, we just work out the absolute uncertainty divided by the measured value, because it's a single value. We're going to multiply that by 100, and this gives a value of 1.8%. Now, this means, because effectively what we have here is we have a standing wave in a string, like this, okay, and a node is a position where we have no displacement. Okay, excuse my poor my diagram. Now it says here that the distance between nodes was equal to 22 centimetres, and that's actually equal to half a wavelength. Now the total wavelength would be similar to about 44 centimetres, but the percentage uncertainty is going to be the same as 1.8, because what we're doing is this distance that we've measured here is equal to lambda over 2. All we've done is we've multiplied that value by 2 to get a value for lambda, but the percentage uncertainty in that measurement is going to stay the same because it's a percentage. And therefore 1.8 is the same value here. Okay. We then have a van undergoes a collision where it decelerates from an initial velocity of 12 meters per second to a final velocity of 4.0 meters per second in a time of 400 milliseconds. So the force is going to be equal to the rate of change of momentum. So that's equal to the change in momentum, which is 4,500 kilograms times 4 minus 12, because that's the final velocity minus the initial velocity. And that's divided by 400 times 10 to the minus 3 seconds to give the size of the force as 90,000 newtons. Okay, so we're not interested so much in the direction. I suppose this really would be a negative value because of the way that force is acting to slow something down. But the size of the force is equal to 90,000 newtons. Okay, so that's just looking at Newton's second law. On the 12th, what result should be recorded for x? So we've got 5 values here. Now the value that we should record is going to be the mean value. So we're just going to add them all up, divide by 5 to get 0.41 millimeters. Now the percentage uncertainty is going to be equal to half the range, because we go from 0.38 to 0.42. So half the range is 0.02. The mean value was calculated as 0.408. Times that by 100 to get 4.9%. So I would quote my value of x to 2 significant figures, like the data here, and the percentage uncertainty is equal to 4.9%. Okay, we've got another experiment calculating standing waves on a string. Here the distance between 5 nodes was measured as 88.3 centimetres. So this is basically a wave that looks like this. Okay, now again, you might not know much about standing waves at the moment, but you can always look in your textbook, you can look at some of my videos, you can Google it. But what we're saying here is that, oh, here we go, so 1, 2, 3, 4, 5. Okay, ignore the last bit there. Okay, we've got 5 nodes, and that was measured as 88.3 centimetres. Now here, The uncertainty was 0.4, which was exactly the uncertainty that we had last time. But now what we're doing is we're not just going to measure here to here, we're going to measure 4 waves in total, or 4 half waves in total. Now the percentage uncertainty, so we've got our uncertainty, we've got the measured value, and that's equal to 0.45%. And that means the uncertainty in the calculated wavelength is going to be exactly the same as 0.45. So what we can see here is that we've got maybe the same kind of wave, but now, because we've measured over multiple waves to get a bigger distance, even though the absolute uncertainty in the measurement is still 0.4 centimetres, we can see we've reduced the error in the measured value by going from 1.8 down to 0.45%. Number 3, looking at an oscilloscope. Again, we've got each of these squares on the y-axis is equal to 5 volts. And I reckon this goes up about 2.6 squares. Each is equal to 5 volts, so that's about 13 volts. The frequency, 1 over the time period, giving a frequency of 3.3 hertz. What results should be plotted for this? Well, I think we have a clear anomaly of 6.1, so I've discarded that. When I work out the mean value to 2 significant figures, it's equal to 9.5 centimetres. The uncertainty is going to be half the range, and we go from 9.4 to 9.8. So half the range is 0.2, divided by the mean value, which I calculated, gives an uncertainty here of 2.1%. So what we've done here is we've discarded that anomalous value in the middle. Now, number 2, the reason I put this in was to get you thinking, and if you found this enjoyable, then you will really enjoy doing the British Physics Olympiad. I say enjoy it, it's definitely a challenge. It's really, really different to the kind of questions you might get in mock exams, and it's really designed to get you thinking. Now, this one over here used nothing more than GCSE knowledge. What we're effectively saying is that at the start, we've got some potential energy stored in this mass here, and we can say that's got 0 potential energy in respect to that kind of ground level here. Now, when it's released, it's going to slide down, and that potential energy stored in the gravitational store is going to be transferred to the kinetic energy. Okay, and if we equate the two things together, we can work out not only the final kinetic energy, but therefore how quickly it's moving. Now, the question I thought was, how high is this mass over here? So what height is this at? Well, the height it's at is going to be the same height above this part here. And what I've drawn that bigger. Now, it says there's a separation between the two things which is equal to 1/8 of the circumference of that circle. Okay, now if that's 1/8 of the circumference, that means this angle in here, theta, is going to be equal to 45 degrees. Okay, so now we have a triangle where we've got a 45-degree angle here. We know this side here is 3.4 because that's equal to the radius of that circle. And we know this height here is also equal to 3.4. Now, if I think about, maybe just put my hand over there, we've now got a right-angled triangle where we know the hypotenuse and we know the angle theta, and we want to work out this adjacent side in here. Now, we can do that by using cos to find that this adjacent side is equal to 2.404 metres. And if we know that this side is I'm just going to write it here, 2.404. If we know the length of this side, and we know the total height is 3.4, the height here is equal to 3.4 minus 2.404, which equals 0.9958. Okay, so we know the height of that mass above ground level. We can then equate the two things together to say that the initial potential energy is equal to mgh, and that's equal to 1/2 times 2mv squared, because initially all of the gravitational potential energy store was due to this single mass here, but when the two things start moving together, their total mass is going to be equal to 2m, because we've got this mass and that mass together. So the kinetic energy is 1/2 times 2mv squared. The m's cancel. We've got a half times 2, so that's just 1. So we can say that GH is equal to V squared. V is going to be equal to the square root of GH. G is just 9.81. H is what we calculated over here. So if we put the numbers in, we can then work out that V is equal to 3.1 meters per second. Now that question is tricky, but it's only based on what you know from GCSE. We're saying that we've got conservation of energy. The initial gravitational potential energy of this is all transferred to the kinetic energy of the total system. If we work out the height, that's just using some trigonometry and stuff that you'll have done in GCSE maths, and therefore you can get an answer of 3.1. A lovely, beautiful question. If you like that, speak to your teachers and maybe think about doing the British Physics Olympiad. There's no downside to doing it. It maybe takes an hour of your time to do some physics questions like this, but you can achieve a lot very soon. 14th of November, you get the score here. Basically, we've got some values here of 0.42, 0.46, 0.41. The context doesn't really matter too much, but again, if you're going to be looking at maybe the Young or the Young's modulus of copper, you need to make sure that you measure the diameter of a wire in at least 3 places. That allows you to kind of confirm it's actually roughly circular in cross-section, and you can see that the more measurements you take, it reduces the error or the percentage uncertainty in your reading. So I've worked out the mean value, displayed at 0.43, half the range 0.025, giving a value of 5.8%. Okay, complete the following sinusoidal curve. Well, you can just do that yourself. Again, if you're going to be doing this in your book, I would suggest using a pencil. And what you can always do is you can move the page. So, for example, you're always completing the curve with your hand on the inside of that curve, and that will give you a much smoother line as you complete that. Now, this is not a smooth curve, but this is the kind of thing that you might expect to see on a real oscilloscope trace, maybe if you're measuring something. It's not always going to be that beautiful sinusoidal curve that we have up here. Again, though, the amplitude, we can look at the total number of small squares, multiply it by here the Y gain of 1.0 to get 3.8 volts. Frequency, 1 over time period. And again, I reckon it's about 4.1 small squares. Each is 5 milliseconds, giving a frequency of 49 hertz. So it's not exactly 4. I reckon it's a little bit more than 4 looking at that data. Okay, 15th. We now have something about adding uncertainties. So this is looking at the absolute uncertainty in values, and what we can do, we can add them together or even take them away. But effectively, even if you're taking these readings, maybe looking at maybe a thermometer, and we want to maybe look at the difference between 2 temperatures, we'd still add on each individual measurement to look at the total absolute uncertainty. Okay, so spring was 5.2. Its final length is 8.3. The uncertainty in the ruler is plus or minus 1 millimeter. Now the absolute uncertainty in each measurement is going to be 1 millimeter. So all I'm doing is just writing down that data here. The extension of the spring is how much longer it's got, which was 8.3 minus 5.2, which is 3.1 centimeters or 31 millimeters. The total uncertainty in the extension was going to be the uncertainty in the initial value added to the uncertainty in the final value, which is going to be this value here multiplied by 2. So that's going to be 1 plus 1, which is 2. That then means, in this example, because the uncertainty was 2 millimeters and the measured value was 31 millimeters, the percentage uncertainty is going to be equal to 2 divided by 31 multiplied by 100, which equals 6.5%. Okay, number 2 is just a definition of Hooke's law, kind of related back to the extension of a spring. We can say that the force is proportional to the extension, provided the elastic limit is not exceeded. Sometimes also known as the limit of proportionality. Fairly similar limits. 16th, again, we've now got a piece of wire which is being stretched. Now the absolute uncertainty in each measurement is 1 millimeter, and again this has been given to us in the question. So often if we're looking at absolute uncertainties in exam questions, they will quote the number they want you to use. So that's 1 millimetre. The extension of the wire in millimetres is 971 minus 942, which is 29 millimetres. The total uncertainty is going to be the uncertainty at the start added to the uncertainty at the end, which is 1 plus 1, which is 2 millimetres. And again, that means the percentage uncertainty in the extension is going to be our uncertainty in the value of 2 millimetres divided by the extension of 29 to give 6.9%. Okay, define tensile stress. So this is something that you might do often towards the end of year 12. So stress is the force exerted per unit cross-sectional area. The strain is the extension of an object divided by the original length. And the Young modulus, or the Young's modulus, is the ratio of tensile stress to tensile strain. So stress, we often use this symbol here. Sigma is equal to the force divided by the area. The strain, we use epsilon, and that's maybe equal to the extension divided by the original length. And then the Young modulus is equal to the stress divided by the strain. Okay, but again, you're going to cover lots more of this if you haven't already seen it in your textbook or in the videos that I've made. Convert the following quantities into standard SI units. So I've just displayed these in standard form. So 6.30 times 10 to the minus 7 metres and so on. I converted millilitres into maybe cubic centimetres, which I then used to convert into metres cubed. Converted light years. And again, you can just Google this if you're not sure about it. You probably don't remember how many metres are in a light year, but I just did 4.25 times the number of metres in a light year. And then 30 miles per hour, if we know the distance for a mile, which is 1,609 metres, we know the number of seconds in an hour, we can work out this as 13.4 metres per second. You don't have to remember this off the top of your head, but it's useful to know how to find that information. Now we've got a pendulum. It's going to make an oscillation, and the time was recorded as 0.8 seconds with an uncertainty estimated to be 0.2 due to human error. Okay, so if you just record a pendulum swinging once, then the uncertainty is going to be 0.2 divided by the measured value of 0.8 times 100 is 25%. That is a massive error. So what we can do, we can improve the experiment by taking the time for 10 oscillations. Now here the value of 8.2 seconds was recorded with the uncertainty of 0.2 seconds. So again, it's the same absolute uncertainty, but now we're doing it for 10 values. So here, the percentage uncertainty was 0.2 over 8.2 times 100 is 2.4%. We can see the difference between these two values is massive. And that's why if you're timing something, you don't just time it for one oscillation, you time it for at least 10 oscillations. Another group carried it out. They looked at these values when they recorded the time for 10. So here the percentage uncertainty is equal to half of the range divided by the mean value. Because now what we're looking at is the percentage uncertainty in repeated readings rather than a single reading like we had for A and B. And when they did that, they found that the uncertainty was now 1.0%. So really, by looking at these answers, we can see that doing it for multiple readings is going to give you a lower value for percentage uncertainty. And if you do it for multiple readings, in order to look at the range to take a mean value, that will reduce the uncertainty even more. So here we go. Percentage uncertainty reduces with repeated readings for multiple oscillations. Okay, remember that when you're doing practical work. Okay, this question here came originally from a British physics Olympiad question. I adapted it slightly, just rewrote it a little bit. But basically, we've got something to do with moments. Now, this one over here, I thought came out with a beautiful answer, but I did a couple of things here. First of all, I've got the pivot in the middle, and we've got this distance A and this distance B. So this distance A is different to distance B. Now, initially, when an object mass m is to be measured, when placed in one pan, the balance is levelled with m1 in the other pan. Okay, so I just drew that out. And then I said that if it's an equilibrium, then the total clockwise moments are going to be equal to the anti-clockwise moments. Now, the clockwise moments really would be equal to the weight, which is the force down, times the perpendicular distance from the pivot about which we're taking moments from. Now, effectively, that would be mg, and that would be m1g over here. But because we've got g on both sides, I didn't write it down, because effectively we'd have mga, m1gb, because that's now the mass converted into the weight, but obviously the g's cancel. And so ma equals m1b, and therefore a over b is equal to m1 over m. Okay, that's good so far. We've then got the same over here, but now if you've got the mass at this side, we've got m2 on this side, so we've got m2a is equal to mb. Again, it's an equilibrium, so we've got the anti-clockwise equaling the clockwise moments. I've rearranged this to say that a over b is equal to m over m2. And then I've equated this with this, because both of these, m1 over m and m over m2, are both equal to a over b. And therefore, m1 over m equals m over m2. If I kind of cross multiply and all that kind of good stuff, we can say that m squared is equal to m1 m2. And that means m is equal to the square root of m1 m2. So it all kind of ends up quite nicely. So that's the expression that relates the mass to m1 and m2. Let's try that. So imagine m1 was 1.22 kilograms, m2 was 1.9 kilograms. What would be the value of m? Well, it's just equal to the square root of these two numbers multiplied together, which when you do the maths is equal to 1.52 kilograms. So this is how we can use this lever balance to work out an unknown mass. Hopefully my explanation works okay. So that question there, again, is just based on your GCSE knowledge about moments and equilibrium. On the 19th of November, the first thing is we have even more information, and this one is about combining uncertainties. So we might have different measured values in an experiment, and we want to look at the total uncertainty or the combined uncertainty of those individual measured values, maybe when we're working something else out. Now, ultimately, the rule is that every time you see that measured value or quantity in an equation, you just add it on to the others. And this is just a way of estimating roughly the total uncertainty in your final answer. So here are the rules here that you're going to be familiar with. It tends to be that, the more practice you do, the better. And I think you probably wouldn't get anything like this last one here. But effectively, every time you have something, you add on the uncertainty in your value. So we've got the uncertainty, percentage uncertainty in the current, percentage uncertainty in potential difference. And we want to look at the percentage uncertainty in the calculated value of resistance. Now R is just equal to V divided by I, and that means the percentage uncertainty in R is equal to the percentage uncertainty in V added to the percentage uncertainty in I, which is equal to 4.9%. If we wanted to look at the uncertainty in the power, well, that's equal to V multiplied by I. And again, even though that was divide and that was multiply, what we're doing is we're still adding the individual percentage uncertainties again to get a value of 4.9%. So this is just a rough way of estimating the uncertainty in the resistance or power in this particular example. Now we've got something which is a little bit more complicated. We've got a few more examples here, current, PD and time. Again, the resistance is equal to V over I, and therefore we're just adding this value of 1.7 for the potential difference to the percentage uncertainty in the current, which is 4.7, to get a value of 6.4%. Now the energy transferred is going to be equal to I times T times V. So the percentage uncertainty in this is equal to the percentage uncertainty in I, added to the potential uncertainty in T, added to the potential uncertainty in V. It's very hard to say, which if we add these three together, gives us a value of 6.6%. And finally, this one over here, we've got measurements to look looking at the diameter, length and resistance, and we want to look at the calculated value of resistivity. Now resistivity is RA over L, and therefore we're going to add up the uncertainty in these measurements. But of course the percentage uncertainty in the area, because the area of a wire is equal to pi d squared over 4, or you could say that the area is equal to pi r squared. Well, the uncertainty in the area is going to be equal to twice the uncertainty in that measurement for the diameter, because pi is a constant value, so is the number 4. And if you looked at the percentage uncertainty in the radius, that would be the same as the percentage uncertainty in the diameter. So here, to work out the total uncertainty in the resistivity, we add on the uncertainty in the resistance of 1.3 to 2 times the uncertainty in the diameter, added to the uncertainty in the length, which gives us a value equal to 6.3%. For the 20th of November, the first thing we can do is look at the mean value of these numbers, which are given as 0.100 kilograms to 3 significant figures, like the data there, which I think is appropriate. Half the range is 0.03 divided by that mean value, gives an uncertainty, percentage uncertainty of 3% in that data. We then have the size and direction of the resultant force. Again, draw this in, maybe with a ruler, just to get you a rough idea of what you're looking for. We've got perpendicular forces. We can work out the size of the force by using Pythagoras. So 12 squared plus 15 squared. Square rooted is 19 newtons. And the angle theta, which I've labelled here, I've said is equal to, again, thinking about maybe a triangle up here. We know the adjacent side, we know the opposite side, and therefore we can work out theta as 51.3 or 51 degrees. Okay, so that one there, simple, just using Pythagoras and a bit of trig. This one over here, a little bit more complicated. The amplitude was okay to work out, because I guess this is about 2.8 small squares, each is worth 0.1 volts. The time period, I worked out from the peak to the trough, and I looked at how many squares that is. So I would say from the peak to the trough is going to be half a wavelength, and that's equal to 9 squares. So 9 times 2 means that we've got 18 squares for a wavelength. Each is worth 5 milliseconds. So you can see whoever set this up hasn't really adjusted the time base properly. Really, they should have adjusted the dial to the right to get maybe a complete wave within that. But this gives a frequency of about 11 hertz. Okay, the 21st. Plastic behaviour is when a material will permanently change its shape once a load has been removed, whereas elastic behaviour, once you remove that force, it's going to go back to its original dimensions. It's going to go back to its original shape. Right, this one over here is another Olympiad question where you get quite a crazy answer. So we've got some information here about resistance and how that's related to resistivity, the length and the area. We've then got some data for copper. We've got the resistivity of copper, and we've got silicon, which is a semiconductor, has a very different resistivity of 0.53 ohm meters. So about 10 to the 8 times bigger. Now, if you had a copper cube of length a meter and cross-sectional area a meter, the resistance between opposite faces would be 1.68 times 10 to the minus 8 ohms. We know that because if you know the resistivity, the length and the area, then that will give you the value for resistance. If you had a cube of silicon and it had the same low resistance, how big would it need to be? Well, first of all, it's a cube, so we know that the volume is equal to L cubed and the area is equal to L squared. We know the resistance is equal to rho L over A, but the area is equal to L squared, and therefore that's equal to rho L over L squared. These cancel, and therefore the resistance equals rho over L. Now, what we can do is, because we know R is equal to rho over L, we can rearrange this to make L the subject, and that's equal to rho over R, which is what I did here. So the length of that silicon cube would be equal to the resistivity of silicon divided by the resistance of that silicon. Now the resistivity has been given to us up here, 0.53. The resistance is 1.68 times 10 to the minus 8, which is given to us up here. And when you do that, you find that actually the sides of this cube would be 3.15 times 10 to the 7 meters, which is a really large number. Okay, so this is more theoretical. How big would that silicon have to be to have the same value as that copper? So quite a big answer. But it's really looking at this, thinking, okay, we know this equation, we know the kind of what it would look like in terms of the geometry, relating the volume to L cubed or the area to L squared. And then it's a case of just rearranging that equation a little bit, putting in some numbers to get your final answer. But that one was tricky. However, if you like those things, the British Physics Olympiad could be your thing. 22nd, we've got the percentage uncertainty in maybe the force. Okay, so we know that the force on a wire perpendicular to a magnetic field F is equal to BIL. That's something that you did at GCSE. So this is using GCSE knowledge. The percentage uncertainty in the force is going to be equal to the uncertainty in the strength of that field, added to the uncertainty in the current, added to the uncertainty in the length. And when you do that, it gives an uncertainty of 7.4%. I've now got this equation here. This equation here you might not be familiar with, but this is to do with the time period for an oscillating spring mass system. Now, you don't need to know that to actually do the work, but the first thing I'm going to do is square both sides. So we can say that t squared is equal to 2 squared, which is 4, times pi squared times m over k. We can then bring the k up here and bring the t squared down there to say that k is equal to 4 pi squared m over t squared. So this would mean if you knew, if you had a spring mass system, you knew the mass that was oscillating, knew the time period for an oscillation, you could actually use that to work out the spring constant. We now have 4 sketches. This is for the standing or stationary wave formed on a string fixed at both ends, the kind of thing you might have seen at GCSE, where you've got that string oscillating in the lab. Now, sometimes this is called a standing wave, sometimes it's called a stationary wave. These words mean the same thing. Now, the first harmonic, we have a node at each end, and we have our maximum amplitude in the middle. The second harmonic, we've got 3 nodes, 1 at each end and 1 in the middle, and here the length of that is equal to a wavelength. We then have 4 harmonic. We then have 4 nodes, and it's always good to draw the nodes in first, and then just complete the diagram afterwards, and then we've got our 5 nodes there. So those are the first 4 harmonics for a standing or stationary wave in a string. On the 23rd of November, we've been given uncertainties in the mass and time period. We want to look at the percentage uncertainty in K. So the first thing I've done is rearrange it to make K the subject, which is what we did yesterday for question 2. Now that means the percentage uncertainty in K is going to be equal to the percentage uncertainty in M added to 2 times the uncertainty in T, because we've got a T squared. Now there's going to be no uncertainty in 4, and there's going to be no uncertainty in pi squared, because that's just a constant. So here we're going to add 0.2 to 2 times 1.3, which gives a value of 2.8%. We've now got another question where we need to do some rearranging, and this time we want to make G the subject. You can see these 2 equations are quite similar, and this is actually to do with an oscillating pendulum. So writing it out, we're going to square both sides. So t squared is 4 pi squared L over G. Going to bring the G up, the t squared down to say that G is equal to 4 pi squared L over t squared. Now that means if you've got a pendulum and you know how long the pendulum is and you know how long it takes to oscillate, we can use that to find the gravitational field strength or the acceleration due to gravity. Okay, we now have standing or stationary waves formed in a tube open at one end. Now effectively, at the closed end, we have a node, and at the open end, we have an antinode. So that's always going to be the case in each of these examples. So we always have a node here. Now in the second harmonic, the first harmonic, we go from a node to an antinode, and that's 1/4 of a wavelength in that pipe. The second harmonic, if there's a node there and an antinode there, there must be a node here. And that node is going to be 2/3 of the way up that tube. So effectively, the length of the tube is going to be equal to 3/4 of the wavelength of that second harmonic. And then I just found it easy to kind of draw in the nodes each time, and then you can just sort of connect them up as you do these patterns here. So those are the standing stationary waves formed in a tube open at one end. There should be a 24th somewhere. Okay, here we go. Right, the 24th. Now you can see what's happening. We've got the uncertainty in length and uncertainty in time. We've been given this equation here, and we want to work out the uncertainty in G. So I've rearranged it. Again, there's going to be no uncertainty in 4 or pi squared. So the uncertainty in G is going to be equal to the uncertainty in L plus 2 times the uncertainty in T. So that's 1 plus 4.6, which is 5.6%. So if you're using this to maybe look at the gravitational field strength, depending on the uncertainties, or the percentage uncertainties in your measured values, that's going to give you a combined or total uncertainty, in this case, of 5.6%. I've now got an unfamiliar equation. Just rearrange it again. You should be good at rearranging by now. You've had plenty of practice, I'm sure, in class. So we've got these different things here when we rearrange it for R, for V, and for eta, a different Greek letter you might not be so familiar with. We now have a tube open at both ends. Now, if it's open at both ends, there's going to be an antinode at each end. And here, for the first harmonic, there'll be a node in the centre. So the length of this tube is going to be equal to half the wavelength. Again, we're going to have an antinode at each end in each of these cases. And when I did this, I would draw either a node in the middle, we'd have 2 nodes, we'd have 3 nodes, or we'd have 4 nodes. And then I just finished off that pattern for the second, third, and fourth harmonic. Okay, 25th of November. Draw a straight line of best fit for the following data. You can do this. Don't try and always force that line of best fit through the origin if it doesn't go. For A and B, I just use a ruler, and you need to make sure that you use a pencil. If there's an anomaly, you can just maybe circle it or discard it and not try and fit the line through that. For these ones over here, we've got some error bars, and that means your line of best fit should go as centrally through all of the error bars as possible. Okay, so that one over there, do it on a bit of paper with a ruler and a pencil. Now, for these ones, we've got a line of best fit which goes as close to many of the points as possible. And I wanted you to draw in a worst acceptable line of best fit. Okay, now this is a line that still goes through all of the data bars, or the error bars, sorry, but it's the one that is the most extreme. Now it could be either shallower or steeper, it doesn't really matter which, but you can see that the lines that I've drawn in green here still go through the error bars, even though it's not a great line of best fit. But that is our worst acceptable line of best fit, or the worst acceptable line. So I did it for these over here, and that's going to be really useful later on. Now this question on the 26th of November initially looks quite tricky. So what we have is basically a block on a slope, and we can maybe think about where the centre of mass of that object is. Now friction stops it sliding down, and we want to write an expression for the maximum angle on the slope that the block will remain upright. Now effectively, if you've got a stable situation like this, where it's maybe on the flat, the centre of mass, or the centre of gravity, is going to be inside the base. It's going to topple over though when that centre of gravity is going to lie outside of the base. And so there's going to be a certain point where the centre of gravity here is going to be directly above that corner. Now at that point, we now have a right angle triangle where this is W, the width, we've got the height of that, and this is at an angle of theta, and that angle theta there is going to be the same as this angle theta, which is the angle of that slope above the table. Now, if we think about this triangle here, we want to know theta, we know the adjacent side and the opposite side, so that's the opposite side there, and that means tan theta is opposite over the adjacent, or theta max is going to be tan to the minus 1 W over H, the opposite over the adjacent side. Anything beyond that, and the centre of gravity is going to lie outside the base, and this is going to topple over that rough surface. Hopefully that makes sense. The second part is even more tricky, but you can get there. So what we have is basically two things where we've got a square on top that's going to wobble side to side. And it's going to wobble through a range of angles without actually tipping over the edge and actually coming off. So we know the length of the side is equal to r pi over 2. Okay, and that means half of the length from here to this point over here would be equal to r pi over 4. Now, this can move through a distance of s from the centre point to the point where that centre of mass, or the centre of gravity, is basically vertically above that tipping point. And that's going to be when it moves through this angle like that. And that means this distance here, s, is equal to the length of half the side of that square. Now, because the length is equal to r pi over 2, L over 2 is equal to r pi divided by 4, and that's equal to this section of that circle S, and the angle theta is equal to S divided by r. That's if we maybe think about this angle theta in radians. It's the arc length divided by the radius. And so when S is equal to r pi over 4 divided by r, that means that the angle theta is equal to pi over 4 radians, or 45 degrees. Okay, now that means the full angle isn't just 45, but it's going to be double that, which is equal to 90 degrees, or pi over 2 radians. Hopefully, despite my maybe kind of poor explanation of that, you kind of understand the geometry of how that can basically get to a point there where the centre of gravity is still not actually over the base of that shape and it would topple off. Instead, it would then go back to the other side and back again. Hopefully that makes sense. Right, that was the 26th of November. If you like those questions and you can explain them better than I can, don't forget to maybe think about doing the British Physics Olympiad. And yeah, challenging yourself with some proper physics. Okay, 27th of November. Write the following derived units in terms of their base units. So a coulomb, well, we know that charge is equal to current times time. Current is amps, time is seconds, so a coulomb is an amp second. And I just use square brackets to show, and also a green colour here to show that these are our base units that we're looking at. The Newton, well, force equals mass times acceleration. So a Newton can be expressed as a kilogram times a metre second to the minus 2. So that's kilogram metre second to the minus 2. A joule, well, we know that energy, we can maybe express it as, well, work done equals force times displacement. The force is measured in newtons, which is what we had up here. So that's kilogram metre second to the minus 2. We're going to multiply it by the distance or displacement in metres to give kilogram metre squared second to the minus 2. Now the volt is the work done per unit charge. Okay, and therefore the work done is this one over here, kilogram metre squared second to the minus 2. Charge, we've already worked out here as amp seconds. And when you divide this by that, we get kilogram metre squared second to the minus 3 amp to the minus 1. So this is the SI base unit for the volt. Okay, right, amplitude and frequency of the signal on the oscilloscope. Well, again, I reckon this is about 2.8 squares up. Each is half a volt, so that's 1.4 volts as the amplitude. Frequency is 1 over the time period. I reckon the time period here is equal to 4.5 squares times 100 milliseconds to give a frequency of 2.2 hertz. 28th of November, again, you're going to be drawing some worst acceptable lines. Now, these still need to go through all of the error bars, and they can be steeper or shallower than the line of best fit. So this is sort of what I came up with over here. You'll notice actually for A and B, they've got a fairly similar gradient for the lines of best fit, but when you've got larger error bars, we're going to have a much bigger difference in the gradient and the y-intercept of that worst acceptable line. So we did that for part 1. For part 2, you just had to draw in your line of best fit as well. And again, the line of best fit should go as close to as many of the data points as possible. and the worst acceptable line can be steeper or shallower, but it still needs to go through those error bars. 29th November. A simple experiment is carried out to find the acceleration due to gravity g by freefall. This is something that you should be familiar with as one of maybe the required practicals you need for A-level physics or AS-level physics. Now, we've got a ball released from a height measured as 80 centimetres with an uncertainty of 1 millimetre. So here's some data. Calculate the mean value of t. We're looking at this. I'd say the values are fairly similar, so we're just going to add them all up and divide by 5. And therefore, I'm going to give my answer as 0.43 seconds. Okay, fair enough. If air resistance is assumed to be negligible, calculate the value of g that this data suggests. So I'm going to write out suvat, because we've got an object which is moving in that kind of one dimension. So we've got suvat. We know the height is 0.800 metres. We know initially it was at rest, and therefore u is 0. We know the acceleration is due to the gravitational field strength, and that's equal to g. And the time was 0.43, which we got from up there. We can use this equation, s equals ut plus a half at squared. U is 0, so that goes to 0. And if we rearrange this to make a the subject, we can say that g is equal to 2s over t squared, which is 8.653, so about 8.7 metres per second squared. Now that, to me, seems like an appropriate value because we know it should be about 9.81 if there wasn't any air resistance. So 8.7, about 9, is a fairly good close value. Now, the percentage uncertainty in the recorded data for height and time. Now for the height, it's 80 centimetres or 800 millimetres with an absolute uncertainty of 1 millimetre. So that single measurement will give an uncertainty of 0.13%. So the uncertainty in the height is going to be very, very small. Now for the time, because we've got repeated measurements, we need to look at half the range, which is 0.47 minus 0.40 divided by 2, divided by the mean value, multiplied by 100, gives an uncertainty in the time of 8.1%, as there are percentage uncertainty in these multiple readings. So that's the uncertainty in the height, and that's the uncertainty in the time, the percentage uncertainty in the height and time. Now, the percentage uncertainty in the final calculated value of g, well, we know that this is equal to 2s over t squared, so we're going to add the percentage uncertainty in s to 2 times the percentage uncertainty in t, because we've got a t squared over here, and the 2 doesn't count for anything at all in this. So that's 0.125, which is the value for that, plus 2 times 8.14, the value for that, giving an answer of 16.4, or about 16%. So what this means is that the total percentage uncertainty in our measurements was 16%. Now, the uncertainty in my value of g is going to be equal to my value that I actually recorded over here, multiplied by 16%, which is 0.164, which equals 1.42. So what this really means is our value for g was 8.7 metres per second, plus or minus 1.4 for our value. Now that means, because of the error in our measurements, the value of g could really justifiably be between sort of 7.3 and 10.1 metres per second squared, which means that that's why this number wasn't exactly 9.81. So that's the uncertainty in our value of g, 1.4 metres per second squared. 30th of November, the last day of the month. What is equilibrium? Well, something is an equilibrium when the forces on it add up to 0 and the total moment adds up to 0 as well. So we can say that the resultant force, or the sum of forces, is 0, and the sum of moments is also equal to 0. Number 2, have a go at the curve. You're good at this stuff now. Again, move the paper if you need to get a lovely smooth curve as you're drawing it. These sine curves and cosine curves come up all the time. And then we've got the standing or stationary wave formed below. So when a string is fixed at both ends, we have a node at the ends, and this is what we see. When you've got a tube open at one end, we've got a node and an antinode, and a tube open at both ends will have an antinode at both ends. So those are the fundamental frequencies of standing wave in these three scenarios. So that is November. Hopefully that's been okay. There's a lot of good work there. If you're doing this book now, keep at it. I guarantee if you're doing questions every day, or maybe doing a load of questions on the weekend, you're going to find the rest of A-levels so much better. So those were my worked solutions, or me just basically chatting and just going on and on about stuff. But hopefully that's helped if you found some of my worked solutions weren't that clear. So there we go. Those are my answers for November.